Welcome to today's webinar. The topic today is modeling and design of reinforced concrete slab in Rfem 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, technical content of the website, German and English webinars, customer projects, and so on. I will be the moderator today, and I will answer your questions together with Alexander Meyerhofer. The presenter today is Richard Hase. He works in our customer support team and is also responsible for the product engineering concrete. Alexander Meyerhofer is the head of the product engineering team concrete, and he works also in the customer support team. I say something how you can ask questions, at least for the attendees who participate the first time in the Dlubal webinar. At first, I switch off my webcam that you can see the full screen. If you have a question, just press that button with the question mark, then enter your question here, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Richard. Richard, it's your turn.
Yeah, hello and welcome from my side. And thank you, Andreas, for your introduction. Then let's start with our webinar for concrete today. We have 5 chapters today. At first, I will show you how you can modeling with using a DXF file as background layer, so that you can modeling your model faster and do it in a good way. And the second chapter, I will show you the possibilities of our load transfer options from one to another model. And the third chapter will be our automatic determination of reinforcement. On the one hand for surfaces, and it's also possible for members. At the next point, I will show you our punching shear reinforcement. So when it is not possible, when you increase your longitudinal reinforcement on a surface, you have now the option to choose punching shear reinforcement and to fulfill the punching design checks. And at the last point, I will show you our deformation calculation with nonlinear concrete material. It's relatively new in our program, and I will show you the possibilities, what we can do with the nonlinear concrete at the moment. Okay, then let's switch to our first chapter, the modeling using with a DXF file. We have here 2 options. The first one is to import here our DXF file or files with another data file type, and you can import it in this way. And the good thing on this point is you can direct modify the lines which you have imported from the file. But we will do it today with the background layers. The background layers is fixed in the background, so it's only a visible point, but Rfem can catch some points of this layer, and so it's a help for modeling. Okay, then maybe we go back to our model today. We have here a little building or let's say from industrial areas, and we have a silo on the top. And yeah, we don't want to model the silo. We want to load transfer the loads from the silo feeds, and want to check the surface for the punching design check. So okay, then let's switch first to Rfem 6. Here's our silo, which we have designed and modeled before, and when we calculate it, we have here two load cases, the permanent and the imposed loads, and these loads we want to give on our new model via load transfer. Okay, so then let's start with a new model. We want to model today with a 2D type of model, and we have here two different types for X, Y, one the plate and the other the X, Y 3D. And the difference is in the 3D we also can model, for example, rib members with an eccentricity, and exactly that we want to do today. So we choose this type, and let's call it webinar concrete. And yes, then let's check to the add-ons. The nonlinear material behavior we will add at the last chapter. So let's start with a single concrete design at the first. The standards, we stay in the CEN, so without a national special annex. And I want to show you here some very useful features, our member representatives, and also for the set and our surface cells. Very nice features, but today we want to deactivate them, and yeah, want to start with the model. And let's start with our background layers. It's under guide, objects, background layers. And here you can open this file, webinar concrete. And yeah, the origin point, we let it to the 0 points of the model. And here we have the chain possibility in the DXF file to choose where is here our fixed point. And I have created here the middle of the silo. So okay, then let's import, and yeah, we can start with the modeling. I want to delete all materials which are created before, and yeah, let's start. So today we take European Union concrete, taken C2530, and as reinforced steel we take this B500S and say okay. Here in the area of the cantilever we want to have a rib member, so we create here a section with 24 centimeter to 24 centimeter. Say okay, our thickness of the surface should be 24 centimeter. And yeah, we modeled in the 2D model type, but we want to, considering the height of our line supports and also of our columns. And so in a 2D type, we can do it in the following way. Deleted. We have a fresh model, and yeah, let's define our nodal supports, our columns, and here we have the chance or the option to set the stiffness via a fictitious column. And today we want a circular column, and here you see the conditions, and here we want to have also a hinged end, so we need to switch to an elastic nodal support. Have here a dimension of also 24 centimeter and a height of 2.50 meters. Say OK. For the line supports, it works nearly the same way. Here you must set the coordinate systems to local, and then it's also possible to create a stiffness via fictitious wall. And we take here 24 centimeter and also 2.50 meters. Both ends are hinged. That's what we want. And yeah, then let's start with our surface or our slab. And we want to take here a polygonal form. Our thickness we have chosen at begin. And yeah, let's do it in this way. Okay, now we have our surface. Then let's add some additional lines for this wall, for example. And for the deformation design checks or the deflect design checks, we need to define the lengths which are going into the design check. So I want to show you this for every single slab for their own. Okay, then let's create some points. One side for the zero loads, we need here some points. For the column below the zero, and here we have also 2 columns. Okay. Then, oh, here I forgot the cantilever slab. Okay, but it also functions this way. When you have defined lines on a bigger surface and you want to separate this one big surface to single surfaces, you can click with the right mouse and you have here the option divide surface with intersecting lines. And now you see we have our 3 surfaces, and that's what we want. Here we also want our rib member. Say OK, and we want to design the reinforcement on the surfaces also. So we take 16 diameter with a spacing of 10 centimeter. Okay, take copy 2 times. Okay, then we must go type for concretes. And here we only want this for the surface number 4. And here for our cantilever slab. So we control 1 field, 2nd and 3rd. And now we can go to this rib member. And here we have the chance to define the width, which goes into the section of the rib member. And yeah, we want to choose today the Eurocode 2, which calculate the width on a standardized way. Okay, and what I also want to show you is on the longitudinal reinforcement. You see here the automatic default setting for this section type, and on the flanges the rib member automatically takes information from the designed surfaces which are connected with this rib member. So here it's in gray. So that means when you change here the reinforcement or here, then the rib member automatically will update the informations also here. Okay. Then before we forget that, we want to, okay, let's hit the reinforcement and maybe go to our wireframe model. And yeah, because we are in modeling mode, so that we don't forget, for this 4 nodes from the Zelo load entry, we must define an additional information for the punching design, because here we have only nodal loads without a dimension of the feeds of the Zelo. So a punching design check would give a error warning and would say, okay, here we don't have a dimension for the punching design check. So let's do this here. At first we must activate here the punching design, and then we can create a new configuration. Let's call it Zelo. Go to the punching tab and define here a loaded area for punching node type column, and say we have here 30 centimeter plates, and say okay. Good. Then for the deformation design checks, we also need a configuration for the deflection here. When you go into the edit surface menu, and you have here the surface type you must config. So it is a double supported or a cantilever, and according what you choose here, the limit values are or could be different with national annexes, for example. So you should be here exactly. Yeah, then we have here 6 meter 50 on both sides, so this reference length fit. When we go to this surface, would also choose 6 meter 50, but here we want to choose it on manual way and want selected by 2 nodes, and say okay, the needed length is from this point to this point, 3 meter 75, and the other option for our cantilever slab are the 2 meter 50, but we want here on the shortest or the minimum boundary line and have here our 1 meter, and of course here the type cantilever. Okay. Yeah, that should be with our modeling. And then let's go back to our PowerPoint presentation, to our next menu. We have the options for load transfer via single nodes, nodal loads, line nodes, or we have also a load wizard which simplify the entry, and you are able to select or transport a lot of nodes or lines. And yeah, I will show you these 3 options. And when you transfer a line, you will see these question signs here, and if you start the calculation, then here will stand the right values. So then let's go back to Rfem 6, and yeah, what I forget to say, for this load transfer, it is very important that the models are in the same folder, and therefore you have in the Dlubal Center here some folders, and yeah, you can, for example, here right click connect folder as project, and then you can select a folder, and there in this folder must be all different models which should be connected with loads, and also for our sections, when you want to import the sections, it must also be in this folder. So I have done this before here. So we have a connection for our silo and our webinar model. So then let's go to the loads. So we have here as default setting our self weight, and want to create also a imposed load. Say okay, and now I want to show you, okay, we have here the option to do it via a nodal load. Then you can check here import support reaction, and getting here a new tab, can choose the model, the load case or load combination, and also the option to choose one node here and the load direction. And so you could edit every single point from the other model to our model here and get the loads for this load case. Analog function for line loads. So also you have here import support reaction. Yeah, okay, in our silo we don't have line supports, so that's the reason why we don't see this here. And yeah, we have here the lines, the load directions, the same procedure. But I want to show you a more faster way. It's in our load wizard menu, import support reaction. We take here our silo and have here the import type manually, and here are the 4 nodal supports from our silo. Here automatically see these points here, and you also have the option to switch to free loads. So, or the difference in manually, you have from real node to real node transfer, and for free loads you have this type free loads. So it's not connected on a modeling node. It's more a global coordinate system, and in this system points the loads came as free load, even if you have models which are not complete on one line or have the same geometry. So then this free loads type is very nice. So, but let's change back to manually. Want to choose our nodes here. Our 4 nodal nodes. And also we have the chance here to pick load cases manually. But we want to change automatically, because our self weight is in both models here and the imposed loads both in load case 2, so we don't need to change here something. And we only want to have in the Z direction the loads, and with F8 button on the keyboard we can copy this very fast and say OK. Now we see that we have for our self weight and our imposed load this unknown loads here, and when we calculate, I need to show you, then when, for example, we don't have calculated the silo before, Rfem would start global extrude. So would start to calculate the silo model. And for a moment, what have we done wrong here? We have 2D. Oh, sorry, I have forgot the nodal supports and the line supports. Let's do this very fast. Sorry. No mesh. So okay, our nodes and of course our line supports. So this way, this and this both. Okay, now it looks better. Also, you have an optical control option. you can go to the type for nodes and also for type for lines, and can click here for nodal supports columns, and for the line support the walls. So you have an 3D optical correction possibility to see, okay, if you have entry and height on the wrong way, you would see this here now. But let's go back. Okay, the load transfer also function here from our silo, but now we have also our supports. Okay, and very good is when you choose the loads, for example, on the silo, and save the silo. This model also would see, okay, here have something changed, and these values would be back to an unknown value and would need a new calculation. So you have the actualization option here, or it is implemented. Okay, then let's switch back to our automatic determination of reinforcement. We have the option, how I said before, the longitudinal and shear reinforcement for members and surfaces, and also the optimization of location and length, special for member reinforcement. And when you click this automatic function, you have the option between this parameters. So you click bar diameter or distance. So you don't can do it in an automatic way for both at the same time. So only that you know this. And the same here for the surface reinforcement. You have the chance per direction to choose one automatic function, so for the rebar spacings or for the diameters. Okay, then let's switch back to our model. Go to the concrete design, and before we start with the calculation, I want to open here the global add-on settings, and here we have the configurations, what is to calculate, and we have here the ultimate and the service ability, and as default also the detailing and particular rules are activated. So for example here minimum diameters, concrete cover, and different detailing checks, which is defined in the Eurocode, but we want to deactivate this here also, and want to deactivate the life cycle of results. That means the normal way is when you have a reinforcement, for example, on the surface, and you add some additional reinforcement, then Rfem would say, okay, when you model this, then I need to delete all results and start the calculation on a new time. And we want to deactivate this so we get the results and can add some additional reinforcement. And when we are ready, and then we activate this life cycle again. And yeah, but I will show you what I mean. So then first we have forget the loads. The other loads we have here, all load transfer. but we also need some surface loads. So let's here say 1.5 for self-weight on our three surfaces. Apply and next. Go to the imposed loads. Say here 2 kilonewton per square meter, and say apply next. And on our cantilever slab, we want to have 4 here. Okay, so then we have modeled all our surface loads, deactivated again, and yeah, want to start our calculation with our ULS and SLS design situations. Okay, then let's first start with the reinforcements for surfaces. And yeah, that's my way of working, and I want to show you the good points of that. I start at first all time with the reinforcement checks, and yeah, we have modeled our 16 diameters with 10 centimeter spacing reinforcement, and so we know that. And now we can click on the not covered reinforcement, so we see in the areas where we need additional reinforcement. So let's check this. Okay, then we see we have here some additional. Here we have nothing. Also here and nothing. So we have on the top and on the bottom side reinforcement, additional reinforcement. So, and only in this both surfaces. So then I want to show you the automatic function for, or let's go, we also can do it here for surface reinforcements. Okay, then let's say the rebar spacing should be automatically 7.5 centimeter, and also here 7.5 centimeter, and the same for our cantilever surface. Okay, and normal on the default settings with our life cycle, which we have deactivated, Rfem would say, okay, we will delete all results, and yeah, then you don't have the option to control the rest of the not covered reinforcement. So let's say, okay, we have now our surfaces on for the longitudinal reinforcement checked, and want to look at the stirrups. Okay, I wanna, because I get different results. Sorry, but I need to change here our mesh settings to 30 centimeter. Okay, and let's again calculate. Sorry for that. Okay. Okay, yeah, that looks better. And now we see here we have shear reinforcement for this surface, and nearly every point is in the near of our columns and of the concentrated loads of our silo. And we will check every point as a punching design point. And when the punching is fulfilled, the design check, this stirrup or this shear reinforcement, you can say, okay, it's no longer interesting because we have a punching design check here done, and the priority of the punching design check is higher than the surface reinforcement check. So we don't look at this longer and can go to our members reinforcement, and we want to look at the longitudinal not covered reinforcement and stirrup reinforcement for our rib member. And we see here we have for the stirrup reinforcement we have two less. So let's also do here the distance on an automatic way. Here we have the minimum distance, the maximum distance, and the increments. And let's say, okay. So then we have modeled all automatic reinforcement types. So now we need to activate our life cycle of results again. Say yes. And want to calculate again. Okay, so we see now our member or rib member don't have not covered reinforcement, so that's we are on a good way here. We can deactivate the members, go to the surface again, and now we see here 0, 0 in both directions. Also the same here, here, and here, and how I say the stirrup reinforcement we will check with the design, with the punching design check. So that's not interesting at the moment. Okay, then we need to do one thing for the later calculation of the deformation, and to fix or switch our automatic reinforcement to a normal reinforcement, we can here copy the determined value, and we will do this for our surfaces, and also do this. Here you see the detected distance 20 centimeter at the start was 30 centimeter. So we can determine also this here and say, okay, calculate again. Okay, then the next step, when you have controlled your member and surfaces, with the not covered reinforcement. My way of work is that I go then to the tables and check finally the design ratios. Look for the member. Everything is green and full filed, so that sounds very good. And the same for design ratios of surfaces. So here we have the shear resistance point, but as I say, that's not important now. And also here, also rules for shear reinforcement, but the rest is green and full filed. So we have done our job here. And yeah, let's switch back to our PowerPoint presentation and step to the next chapter, our punching shear reinforcement. And that's the entry options. So you can choose here your material, your bar diameter of the punching objects. And at the time we have the type vertical. And here we will add later different types of punching reinforcement types. The distance we have uniform and different. So you define here the parameter numbers, and then you can define if on every parameter is the same number of this punching reinforcement objects, or you also have the possibility to say different. That's already possible. And the placement we have at the moment the radial form, so that from the center point of the section all get radial. And we also will add other placement types later. But that's our stand of view. And yeah, let's switch back. And yeah, at the beginning of the modeling, we already have the design configurations for our concentrated loads from the silo. And now we need to activate the rest of 3 nodes. Say edit and activate here the punching design, and take here the default setting. That's good. Say OK. And okay, must be fit. Then we start the calculation. Okay, let's go to design ratios of nodes, by node, and see in the table, okay, only one node is not full filed, and that is our center column. And yeah, here we will need an additional punching reinforcement. So let's design here our punching reinforcement. Say create a new one. Take the 10 millimeter, the uniform, the vertical, and define here 5 parameters with 16 legs on each parameter. The distances we let in this way, and say calculate again. And now we see, okay, everything is green. We also can check this by design checks on optical way and see here with values on surface, yeah, that we have every node full filed. So let's again our not covered surface reinforcement and switch to the ISO lines and see here this not covered shear reinforcement for the surfaces are all into the critical section of our punching design checks. So we don't need an additional reinforcement here. So the design check is fulfilled. So this areas we can say, okay, that's nothing. We have checked it with the punching design check. And in the middle, we can see it when we activate the provided punching reinforcement and maybe go back to the ISO bands and see here the the shear reinforcement of the surface, and here our punching reinforcement and over this area. So all points we have full filed and everything is good. Okay, then often we get some questions for the options of showing results. So I will show you this in our webinar too. Often was asked this ratio from the entry load to the maximum resistance value of the shear and as a node surface again, sorry, here. And yeah, so we have nearly for every single design check the options to show the single results and also the ratios. Yeah, that's all possible. And another point which often was asked, that we need not all values on the surfaces or only the extreme values, so that we also have customer points, so that we can define on own way result points, and this is possible. So therefore you must activate here on grid and user defined points, and here we have a shortcut new result points, and when we go to the transparent model, so we have the options really for every result to set these points here. And yeah, for a printout report, for example, it's a very good feature. Okay, and we find it also under the result objects, but let's delete them again. Okay, another feature which was asked and wished often when we go to the serviceability configurations, some design check types are specified to some special design situations. For example, the limitation of steel stress often is to the design situation type characteristic, but in some cases it's also needed that you want to check it for the frequent or the quasi-permanent. And this we have implemented for the stress analysis, crack analysis, and also for the deflection analysis, that you can here choose user-defined assignments of design situation types, and also important for the crack analysis that you can define here for every different design situation type, also other limit values of allowable crack width, so you are very free and for your results and calculations. Okay, that only as information. Then let's switch back. Let's go back to our wireframe model. Okay, and yeah, let's go back to our PowerPoint presentation, and we come now to our deformation calculation with nonlinear concrete material. So we have the option here to consider the nonlinear stress strain diagrams here for the concrete and here for the reinforced steel. And so the material parameters can be considered in this way. And at the time, design checks for deflection and stability are possible. And it's also possible to define user-defined diagrams, but I will show you on the model. Good. Then, yeah, let's start. Maybe we can see at the beginning our deflection. So we have here 0.6 millimeter, and now we want to say the effects of creep and the nonlinear material. So then at first we must activate this add-on, nonlinear material behavior, and want to copy here the creep and copy our materials. Then for our concrete, we need our anisotropic damage model. And yeah, see here, like in the presentation, the stress strain diagram for the concrete. For our deflection design check, we choose here the SLS, but also have other options and can deactivate or activate the tension stiffening, and you direct see here the effect. And you also have the options to export this diagram, config this, and again to import this, so you are free for customized diagrams. And yeah, the creep is activated. Okay, and for our reinforced steel, we need to change the material model also to plastic members, and also have here the chance to switch to another diagram type, but we let it here on the basic and say okay. And now we need to go to the design situations. We take the quasi-permanent, make a copy of this, say here it's non-linear, and we need to create a new combination wizard. So we take a copy here, also call it NL for nonlinear. And what we must do the next is consider the structure modification. And here the member and the surface reinforcement must be activated. Say OK. And change the combination wizard. And yeah, the next what we must do is for our design situation type NL, switch this analysis type to static analysis creep and shrinkage. And we had the option to define the start and the end of the analysis. The default setting here is 50 years. So yeah, we let it and say OK. And would start now our nonlinear design situation, but what I forget. So you can calculate your model with the linear calculation, and then when you copy, so you can calculate your model in linear way with this linear materials, and then you can design a nonlinear deformation, for example, and have here the option different materials, so that only for this design situation the materials will be switched. So then we have here a new tab and say OK, our linear elastic isotropic materials should change for this design situation to anisotropic, and our plastic reinforced steel, say OK. And now we see also it's not any longer blue, so not used, so it's used in the design situation. And yeah, we have 0.6 without creep. And now we calculate with the nonlinear materials and creep for 50 years, the end of analysis, and start the calculation. And see now we have here 1.6. So yeah, we see the difference. And at the moment, the deflect or the deformation calculations with the nonlinear material is only possible in design situations, also stability checks, and are not connected with our concrete design add-on at the time. So, but this will implement it later, but only just for information at the time. Yeah, you do it over the forces and get here the results for the nonlinear calculation. Okay, that should be with my webinar. I will switch back to our PowerPoint presentation and want to thank you for your attention. And yeah, if you have questions, please write us, or ideas, wishes, so that we can look at these mails. And yeah, I hope you have learned something today, and wish you a nice day. and switch back to my colleague Andreas. Andreas, it's your turn.
Thank you, Richard, for your presentation. I have an additional hint to our online courses. For example, the Rfem 6 Masterclass course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design, and the Eurocode 3 course for the steel design with Rfem 6. You can get more information when you click on the button at the bottom, or you can scan the QR codes. Then you get the prices and more information. Okay, that should be also all from my side. I thank you for your attention. Thanks to Richard for your presentation. Thanks to Alexander Meyerhofer for the support by answering the questions. I wish all a nice rest of the day. Bye-bye.